Hello friends, this is Darwin Patel. Welcome to the lecture series of Mathematics-2. In this lecture, we will discuss about the method of variation of parameter for non-homogeneous higher order linear differential equation. In the last lecture, we discussed about how to find the general solution of non-homogeneous higher order linear differential equation. And there are two methods in our syllabus to find the YP, that means particular integral, to find general solution of non-homogeneous linear differential equation. Let us see what is the general solution of non-homogeneous higher order linear differential equation. The general solution of differential equation fn d raised to ny by dx raised to n plus fn minus 1 d raised to ny by dx raised to n minus 1 up to rx given by y equal to yc plus yp, where yp is particular integral and it is depends on only right hand side function RHS equal to Rx. Yc is a complementary function and it is a general solution of corresponding homogeneous linear differential equation. Here, first of all, we find the complementary function yc after converting our differential equation number 1 into the homogeneous form, and using the auxiliary equation of it, we can find the complementary function and then find the particular integral. Here, the particular integral yp depends on Rx and it is obtained by following two methods: method of variation of parameter and method of undetermined coefficients. The particular integral yp is free from arbitrary constant and it depends on only RHS. To find the general solution of non-homogeneous differential equation, we follow the following steps. Step 1 is find the complementary function after converting our differential equation into the homogeneous form, and it is obtained from the auxiliary equation. Here, the second step, we will find the particular integral that is denoted as yp and it is free from arbitrary constant. It depends on RHS equal to Rx. It is obtained from using the method of variation of parameter or method of undetermined coefficients. In this third step, we will find the general solution. It is obtained by y equal to yc plus yp. Let us see method of variation of parameter for the second order non-homogeneous linear differential equation. Let f2 d square y plus f1 dy plus f0y equal to Rx with Rx not equal to 0 be a second order non-homogeneous differential equation where f1, f2, f3 are constants and d is differential operator d by dx. The general solution of this second order non-homogeneous linear differential equation depends on Rx and yc. First of all, we find the complementary function by converting our differential equation 1 into the homogeneous form, and then find the complementary function using the auxiliary equation. Then find the particular integration which is only depends on right hand side function Rx and it is always free from arbitrary constant. Here we have a formula for finding particular integration yp. Here yp equal to minus y1 integration of Rx y2 upon w dx plus y2 into integration of Rx y1 upon w dx, where w is the Wronskian determinant and here Rx is given in the right hand side function and y1, y2 are coming from complementary function. This formula is only applicable for the second order non-homogeneous linear differential equations. Let us see some examples of method of variation of parameter. Here our example is d square y by dx square minus 5 dy by dx plus 6y equal to e raised to x. Here e raised to x is right hand side function and it is exponential function. First of all, to solve this example, we first convert into the homogeneous form and find the auxiliary equation. Here d square y minus 5 dy plus 6y equal to 0 be our corresponding homogeneous differential equation. D is differential operator d by dx and its auxiliary equation is d square minus 5d plus 6 equal to 0. After factorizing, we have a factors of auxiliary equation here d minus 2 and d minus 3 equal to 0. Here the auxiliary roots are 2 and 3. Therefore, our particular solution of homogeneous differential equation is e raised to 2x and e raised to 3x. Here, complementary function is c1 e raised to 2x plus c2 e raised to 3x, where c1 and c2 are arbitrary constant. Now we want to find the particular integral yp. Here, to find the yp, we apply the method of variation of parameter, which is yp equal to minus y1 integration of rx y2 upon w dx plus y2 into integration of rx y1 upon w dx, where w is the Wronskian determinant, y1, y2, y1 dash, y2 dash. Here Rx is e raised to x, and y1 and y2 already obtained from the corresponding homogeneous linear differential equation. Here yp is obtained by this formula, and y1 equal to e raised to 2x, y2 equal to e raised to 3x, Rx is e raised to x. First we find the Wronskian determinant, then find the yp by method of variation of parameter formula. Let us see by calculation how to find the w. W equal to y1, y2, y1 dash, y2 dash. Here y1 is e raised to 2x, y2 is e raised to 3x. Put in the Wronskian determinant, we get e raised to 2x, 2 times e raised to 2x is derivative of it, e raised to 3x is y2, and its derivative is 3 e raised to 3x. Now we solve this determinant, we get 3 e raised to 5x minus 2 e raised to 5x. That means it is e raised to 5x, which is not equal to 0. Here now we calculate the yp by method of variation of parameter. This is the formula for it, and now we calculate it. Here yp equal to minus y1 integration of rx y2 upon w, where w is a Wronskian determinant dx, plus y2 integration of rx y1 upon w dx, where y1 equal to e raised to 2x, y2 equal to e raised to 3x, w equal to e raised to 5x, and rx is e raised to x. Now put in this formula, we get minus e raised to 2x integration of e raised to x into e raised to 3x upon w is e raised to 5x dx, plus y2, that is e raised to 3x integration of e raised to x e raised to 2x upon e raised to 5x dx. After simplifying, we get yp equal to minus e raised to 2x integration of e raised to 4x upon e raised to 5x dx, plus e raised to 3x integration of e raised to 3x upon e raised to 5x dx. That can be rewrite as yp equal to minus e raised to 2x integration of e raised to minus x dx, plus e raised to 3x integration of e raised to minus 2x dx. Now integrate this term, yp equal to minus e raised to 2x into e raised to minus x upon minus 1 plus e raised to 3x into integration of minus 2x upon minus 2. Now yp is finally we have a e raised to x minus e raised to x by 2, that is equal to e raised to x by 2 particular integration. Now finally our general solution is c1 e raised to 2x plus c2 e raised to 3x plus yp is e raised to x by 2, which is obtained by method of variation of parameter, which is our general solution of our differential equation. Let us see second example in method of variation of parameter. Here our example is d square y by dx square plus 4y equal to tan 2x. First of all, we convert into the homogeneous differential equation, that means d square y plus 4y equal to 0, where d is differential operator d by dx, and our auxiliary equation is d square plus 4 equal to 0. Now after solving this equation, we get the auxiliary roots, which are d equal to plus or minus 2i. These are complex roots, so our y1 is cos 2x and y2 is sin 2x. These are the particular solution, and complementary function is c1 cos 2x plus c2 sin 2x, where c1 and c2 are arbitrary constants. To find particular integral yp, we will apply the method of variation of parameter, and this is the formula on the screen. Now we have a formula yp equal to minus y1 integration of rx y2 upon w dx plus y2 rx y1 upon w dx, where w is the Wronskian determinant, y1 y2 y1 dash y2 dash, and y1 equal to e cos 2x, y2 equal to sin 2x, and rx is tan 2x. Here first of all we find the Wronskian determinant and then apply the method of variation of parameter. First of all, calculate the Wronskian determinant, that is here w equal to y1 y2 y1 dash y2 dash. Put in Wronskian determinant, we get w equal to cos 2x. In the second row, we are writing the derivative of it, that is minus 2 sin 2x. Now y2 is sin 2x. Its derivative is 2 cos 2x plus 2 sin square 2x. That is equal to 2 cos square 2x plus sin square 2x. And finally, we have a Wronskian determinant w equal to 2. Now we will find the particular integral yp by method of variation of parameter. Let us calculate it. Yp equal to minus y1 integration of rx y2 upon w dx plus y2 integration of rx y1 upon w dx. Here y1 is equal to cos 2x, y2 equal to sin 2x, w is 2, and rx is tan 2x. Yp equal to minus cos 2x integration tan 2x sin 2x upon 2 dx plus sin 2x tan 2x cos 2x upon 2 dx. Now yp equal to minus cos 2x by 2 integration sin square 2x upon cos 2x. Here we convert tan 2x into sin upon cos, sin 2x by 2 integration of only sin 2x. Here also we convert tan 2x into the sin upon cos, so cos cancel, yp equal to cos 2x upon 2, and that can be written as 1 minus cos square 2x upon cos 2x dx plus sin 2x upon 2. Integration of sin is minus cos 2x upon 2. Now that is equal to minus cos 2x upon 2 integration of sec 2x, that is 1 upon cos 2x, and minus cos 2x. Here cos square upon cos, that means the cos 2x dx, and plus minus sin 2x into cos 2x by 4. Now we have a cos 2x by 2 integration of sec x, that is log sec 2x plus tan 2x upon 2 plus sin 2x, that is integration of cos 2x into cos 2x by 4 minus sin 2x into cos 2x by 4, which is already done, which is the second integration. We will cancel them because they are same. So finally yp equal to minus cos 2x by 4 into log sec 2x plus tan 2x. This is our yp, that means particular integral, and now we put in the general solution. We get the general solution c1 cos 2x plus c2 sin 2x minus cos 2x by 4 log sec 2x plus tan 2x, which is our general solution of our given differential equation y double dash plus 4y plus equal to tan 2x. Method of variation of parameter is very useful to find particular integral when our function is very simple, like exponential function e raised to x, e raised to 2x, etc., as well as sine, cos, simple trigonometric function, and algebraic function like x square, x cube, up to so on. But it is also applicable for tan 2x, x square x, as well as 1 upon 1 plus sine x, e raised to x upon 1 plus e raised to x, like this type of complicated functions. So this method is very preferable compared to method of undetermined coefficients. Thank you very much.